like to turn over the stage to Jim Small. Jim, he was working at CDW, now he's at AT&T. Is that what I heard you say? Okay, Jim's going to tell us all we need to know about IPv6. Take it away, Jim. Thank you.
All right, so I was here a year ago, and I would call it an overview of IPv6 in terms of what's going on and some of the basics. So when I was putting this together for tonight, it's kind of an interesting challenge in terms of what do you talk about for 90 minutes plus. Because I mean, imagine this. So imagine that somebody from outside technology walks up to you and says, okay, I got 90 minutes, why don't you teach me about TCP/IP? You know, I mean, where do you start, right? So I try to take the view of building a lab and then kind of talking about some of the pieces. When I listen to a lot of presentations about IPv6, and there's a lot of things that are not well understood, or people are like, man, this is, you know, why did they do this? Because, you know, it was, you know, the protocol's actually, it's almost 20 years old. So some of it's kind of lost to history. So I'll try to explain, you know, why they did a certain thing or what the thinking was, at least, you know, for that helps things make sense. All right, so feel free to ask questions, and we'll try and take them unless we get short on time. So one thing I didn't want to talk about, and this always happens when I talk about IPv6, that I'll talk a little bit about the why, because I think it's important. You know, in a sense, it's kind of like power. It's one of those things that you don't notice unless it's gone. I mean, you just kind of take it for granted, but if you lose it, it's really annoying. So, but I always get the question when I talk about IPv6, somebody will be like, you know, okay, I understand, like, you know, how to use it and all this stuff, but why? You know, what does it give me? Right? I always get that question. So I try to think, you know, okay, what is one thing that I can talk about that, you know, that will resonate with everybody, you know, something that you can really see that, okay, this is a concrete benefit that we don't have today, you know, and you can kind of see for other types of technologies how this would help. And probably the best example is gaming. So in terms of gaming, if I look at a lot of the new games, they're very interactive. So I tend to have a lot of people playing online games, doing video conferencing, doing multiplayer interaction. And that means that all of those people have to talk to each other over a network. And that creates a lot of interesting challenges that we're going to talk about some of them with the current IPv4. And so if you look at Microsoft, one of their product managers actually says that for Xbox, if you want the optimal experience, you should use IPv6. They've actually tested it, and you will get the best performance using that protocol. Because there's a lot of limitations with IPv4, not that it's a bad protocol, but just because of the scale of the internet, it hasn't kept up, and it's causing a lot of complications. And so it really starts with NAT. So if you look at IPv4, it only has a theoretical limit of 4 billion addresses. And in a world of 7 billion people with, you know, even more billions of machines, it's pretty readily apparent that that's not enough. So, you know, that's been apparent for a long time, so we came up with NAT. The idea of NAT is it's like a PDX. I extend it, I share addresses, kind of like multiplexing. So basically make those 4 billion addresses service a much larger array of people and machines. However, there are some challenges with that. If I want to talk to you and you're using NAT, now I need to use some kind of a lookup service or special method or some way to figure out where you're at, right? Because you're no longer directly reachable. You're going through a gateway. So we usually use something like Stun or some other, or ICE or some other method where people can use a third-party service on the internet, and that allows them to locate each other. So then they can talk directly back and forth. Now, this has worked fairly well up until maybe the last 3 or 4 years, and now this is starting to break down because IPv4 IPv4 is so overstretched that now one layer of NAT is no longer sufficient. So now we have to have multiple layers of NAT. Because again, we're so overstretched that just to keep the internet working, this is necessary. So now we have what's called CGN, which is multiple layers of NAT. And the problem with CGN is it basically makes direct communication almost impossible. So a good example that I've heard of this is somebody will go out and they'll get a home security system. And they have a video camera that they put at home. And that video camera registers with the website, and then they can watch it over the internet. Well, unfortunately, that will not work with CGN. And there's a lot of things like that. If you go through 2 layers of NAT, it breaks that. So there's a lot of challenges with that. And CGN is actually becoming quite prevalent. So if you have Uverse, you probably have CGN. So if you have AT&T or if you have Verizon, most likely you are behind multiple layers of NAT. So that
I've got Uverse and I've got an external IP that has been the same for like
there are some exceptions. So if you had it for a long time, but I can tell you not just with residential. So even with some of the business customers that I've rolled out, AT&T has said we will not give you a public address. You will use a private address, and we said, okay, thank you very much. We're going to go with a different carrier.
Oh, really?
And
So
they said, okay, sorry, we can't help you.
just up until recently, I had an external, IPv4 address. And
It depends on the area, but I have actually had AT&T say, I understand you're going to go with a different carrier, but we cannot give you a public address.
wow.
For this particular, I don't know if that's a CO issue, but I have personally run into that.
Well, so do they have IPv6 yet?
Yeah.
Yes and no. They have a form of it called 6RD. I don't think we'll get that tonight. They don't have it directly like Comcast, but they're working on it. And as far as speaking for AT, so I'm speaking as an individual. As far as speaking for the company, I mean, I just joined AT&T like 2 weeks ago, so.
So it's not all your fault, yeah.
Yeah, and you can blame me in a couple of weeks, but not yet.
they hired you to get IPv6 rolling.
That's it. For other companies.
So I've got to still tunnel then is what we're talking about, right?
Yeah, with AT&T you do 6RD, which is like a tunnel. So so you can, you're right, you can get it with some locations, but with some you can, and Verizon is similar. So, and this is gonna get worse just because there's just not enough addresses, right? You gotta, if somebody calls up a carrier and says, I wanna get on the internet, the carrier's not gonna say, oh, sorry, I can't help you, go somewhere else, right? So the way we're making that work now is we have to have multiple layers of that to stretch it out. So this causes some really interesting problems with gaming, and typically what we have to do is now we have to go through a relay. So here's the challenge of this, is if I have to go through a relay, let's say I am a gaming company. That means that now, in order for people to use my service, I have to set up some kind of a service that they can relay through. And that service has to match the bandwidth of all my users. So all my users that have fiber to the home, that have 100 megabit internet connections, if I have thousands of those, I gotta be able to service all of them through that relay, because a lot of them are going through multiple layers of NAT. So you see how that can get kind of expensive? So this is kind of the hidden problem of IPv4, is everybody thinks like, it's not my problem, somebody else is gonna deal with it. But the challenge is that there's a cost, right? Because in order to maintain all this infrastructure, and here's the other big challenge. If I'm a carrier and I have to deploy CGN to service new customers, how much money am I making on deploying CGN? Yeah, nothing. What does CGN do to my support and operational costs? Does it lower them?
Yeah.
Sure.
No, it actually has a substantial increase. So the hidden cost of IPv4 is all of this is going to cause pressure in terms of margins and prices to go up, because to support all this infrastructure, somebody's got to pay for it. All right, so the advantage of IPv6 is, because it has, for all practical purposes, I don't harp on this a lot in this presentation because, like I said, there's only so much we can fit in. But really, for all practical purposes, IPv6 is an infinite address space. So if you listen to some of the people who do this at the carrier level, who basically deploy it all over the world, IPv6, it's so unimaginably big that what everybody thinks is the technology will become obsolete before we run out of addresses. Right, so look at it another way. If you look at IPv4, it came out in the 60s, right? And maybe it will last another 10 or 15 years. So that's what, maybe a 50-year lifespan? So how many people think that IPv6 is gonna last, you know, a lot more than 50 years? I don't know about that. I mean, because if you look at how fast technology is changing, are you sure that's gonna cut it forever? So I mean, it's designed to last for 100 years, but I don't think we'll make it that long. Kind of the consensus is by the time we get to the point where, you know, we have interplanetary travel or something like that and need more addresses, there's gonna be other technologies, right? Because it's just not gonna work. So if I look at this guy, because I have unlimited addresses, I don't have to use that. I mean, that's not the only reason. So the advantage of that is, if I wanna look somebody up, all I have to do is DNS, right? And even if I have to use dynamic DNS, if I have a dynamic address and it's constantly changing, there's lots of free services. So the cool thing about using DNS is it's already out there. So if I'm a gaming company, I don't have to basically build out infrastructure. Everything I need is there. I just have to write the game, and it just works. Whereas if I'm using IPv4, now I have to maintain all this stuff. So it's not with IPv6. I wish I could think of something sexy. I mean, it's not like a cool new toy that's flashy, but the reason we need it is just for practical reasons. The burdens that we have to bear for IPv4 to make things work are starting to become somewhat prohibitive. All right, so I always like to just kind of briefly mention this. I don't think, in my opinion, I think we're kind of past depletion. Just because if you look at the growth, I think I don't think this is so important anymore. Right now, so in terms of like the free pool for IPv4 is depleted a long time ago. If we look at the 5 regions in the world, Asia and Europe are out, right? They've been out for a while. The US will probably make it about another year. It's hard to say exactly. What does that really mean? Honestly, I don't think it means anything. But this is usually a popular question, so I like to at least throw it out there. But one thing I can tell you is interesting. If you look at ARIN, so ARIN is who hands out public IPv4 addresses for the US and Canada. They have less than 25 million addresses remaining. And if you look at the last couple of years, we've been averaging about 40 million addresses a year. Now, I mean, obviously we're not gonna average 40 million addresses anymore because we don't have it. Right, so that's slowing down because all the major carriers are deploying CGN to basically try and slow that growth and give themselves time to deploy IPv6. So, more interesting though, because this is the real question I get, especially the US, is people say, yeah, the US is a mature market, we don't have a huge, we have population growth, but not a huge population growth. We don't have a huge increase in computer penetration, so in the US, this isn't our problem, right? It doesn't affect us. Well, not really, because even though we don't have the population issue, because our population has fairly high penetration, mobile devices are huge, right? So even look at all the people in this room are totally guilty. How many people only have 3 devices? Not even 1, right? So one of it was the Yankee Group estimated, this might be a little high, but they estimated by 2015 that the average person will have 10 network devices on it. Because you have glasses, right? Your glasses have sensors now, like glass, that's becoming really popular. Clothing, all your clothing has RFID. Like I can tell you, my older son plays hockey. If you have a kid in sports, it drives you nuts, right? So the equipment's expensive. It doesn't matter what the sport is. Hockey, football, dancing, I mean, it's all expensive. So you buy all this nice equipment for your kid, and you would think when they go into the locker room to change, they're all careful with it, right? Yeah, not. So this is the future is gonna be that we have RFID tags that we put in all the equipment. So your son or daughter brings their equipment out and you can literally take out your smartphone and scan it and it will say check or not, right? Check, all the relevant RFID tags are there, or no they're not. That's where we're going, right? So everything is gonna be online, right? That's called the Internet of Things. So we have all these mobile devices, we have the Internet of Things, and the Internet of Things, that's scratching the surface, right? What about the light bulbs? All light bulbs are starting to come online, right? So when I look in a building, I can tell you which light bulbs are burned out, I can tell you how much power they use, I can tell you when they go on and off if they have sensors. Everything that has power is basically gonna come online and into an intelligent sensor network. So that's happening now. There's already a lot of companies that have been doing that for years.
Well,
So
I
you
saw,
have,
just jump
Sure.
in, so there's also like, they're addressable, you can make them change like the color settings, and, you know, blue, red, green, and.
yep. And you know, it makes sense, right? It's a logical progression. We want to be able to manage and control and monitor all these things. But if you look at that, right, the current estimate is by 2020, we're going to have 50 billion things on the network. So 50 billion things, and we have an addressing system designed for 4 billion. Right, so that, and the US is actually a leader. Silicon Valley is the center of all this. Right, so this is very much in the US. So all of this stuff is putting pressure on IPv4. That's why it's an issue. All right, and the other thing I like to show, I really think we're past depletion, and now we're looking at adoption. So if I look at adoption, it's actually picking up quite a bit. And this year we will actually hit critical mass in the US. Several other countries like Sweden have already hit it. But that's when because that's the next big question I get is like, okay, you know, I can see like with gaming, with telephony, with unified communications, you know, I can see how that makes life better. So when are we going to see the killer app? Well, I actually expect to start seeing things in fourth quarter this year because we'll cross 10% by the fourth quarter. So if we look at some of the major carriers, we're doing pretty good. Virginia Tech is probably one of the leading universities, but if you look at most of the major universities, more than half their traffic is IPv6, which means that all of my students that are coming out of all of our major universities, including U of M and MSU, they're basically used to using IPv6, right? So all of these people are coming into our workforce with the expectation of, what? You don't already have it rolled out? I mean, come on. We've been using this in my college, you know, I've been using this in school for 5 years, you know, what are you guys doing? Right, so this is kind of becoming the expectations. If you look at the DoD, they've been running it for over 10 years. Verizon Wireless, so largest cellular carrier, 40% of their traffic is IPv6. So that's pretty significant deployment. Comcast is the largest ISP for residential, they're over 20%. AT&T, they're the largest carrier in the world, they're almost at 15%. And then T-Mobile has an interesting statistic in that if you look at the new T-Mobile handsets, they're actually IPv6 only. So that's an interesting challenge too. So now if I have people on my network with T-Mobile devices, how do they interact with my applications if they're IPv6 only? That can create some interesting challenges too. In the US, it kind of fluctuates, but we're roughly around 6%. So 6% penetration, I mean, it's, you know, it's not huge, but I definitely wouldn't call that insignificant. So that's if I look across the US, that's a pretty decent penetration figure. If I look at weighted content, so this is by the Alexa 1000. If I look at the top sites and I look at what people actually go to, about 45% of it's reachable over IPv6. So it's pretty decent progress. All right, and this, I came up with this a couple months ago, so it's a little out of date, but the other question I get, and you know, then we'll move on to actually setting it up, is you know, yeah, okay, it all sounds good, but when are people actually going to do something? So really, IPv6 is really nothing special. It's just a technology, like anything else. So when I'm looking at any technology, it's all about the adoption life cycle, right? Am I a bleeding edge innovator, or am I one of the people that you have to drag me screaming, right? And you know, we're all different depending on the area. So this is, if I look at the 50% mark, this is what we're looking. And this is based on what Google's seeing. So I think this should be pretty close. So you can see we're gonna cross 10% in Q4, and we'll hit 50% towards mid to end of 2016. So I mean, it's still a little ways off, but I know there's a lot of people that think, you know, it's not gonna happen. They're gonna be mighty surprised in a couple of years. So we're moving along pretty well. And in terms of companies run the gamut. I mean, I can tell you from dealing with this. So there's a lot of companies that are like, you know, I'm not gonna do it, nobody's gonna make me. And you know what? I have a great story. So I can think of somebody in my family. They had a flip phone. They love their flip phone. They hate smartphones. Those smartphones are, I hate those things. You know what? They went to renew their phone. Carrier said to them, I'm very sorry, but if you want to stay with us, you have to get a smartphone. I'm not going to stay with you. Went to another carrier, same thing. Went to another carrier, same thing. You know, you cannot have a cell phone. So, you know, were they happy about it? No. You know, but guess what? Now they have a smartphone because all the carriers say you have to have one. So, you know, there are going to be some people, I expect, that are probably going to wait, you know, 2017, 2018 until they absolutely have to. When basically the major carriers are saying, okay, you know, we're not going to route IPv4 on the internet anymore, and you have to buy a special service from us, they'll be like, fine. So there's going to be people like that, but there's also a lot of people, I can tell you, when I do at work, that are working on it right now. So I mean, it's really looking at this and figuring out, you know, what makes sense for you, and when you look at it as a technology, where do you want to be on the adoption life cycle? All right. So any questions on that? I mean, I don't want to spend too much time, but I'd like to at least give an overview. Yes.
So, you were saying something about you could be using this and it will slow down your connection if you have a faster connection. So I've got a place down in Austin where. Okay, so you're playing a game and somehow it goes based on the CG. What is it? CGN. You're using that. It makes the game playing slower.
So the challenge with CGN. So CGN is just multiple layers of net, and I mean, unless you have an underpowered device, that in and of itself usually isn't going to slow you down. The problem is, if I'm playing, let's look at video conferencing. That's probably the easiest to understand. If I'm doing a video conference with somebody, right, at some point, I have to stream the video into their house. So if they're behind multiple layers of NAT, then it might be impossible to do something directly, which means that that person has to go to a third-party service and pull the video, as opposed to me sending it. Right? They have to go through a relay point.
Okay, all right, so
the
there's delays.
the problem with the relay point is that has a limited amount of bandwidth. Right? So look at it like this. Because this is a common issue with companies. If I'm a company and I have people working from home, a lot of times from a security point of view, I don't want to do what's called a split tunnel. I want all their traffic to come back through me so I can control it. Right? Sounds good. The problem with that is nowadays a slow connection is 10 megabits. So if I have a 1,000 user workforce and half of them are working from home, I mean, the amount of bandwidth I have to support that is prohibitively expensive. Most companies can't afford it.
Okay, so
it's the same thing with the relay, right? If I have to relay all that traffic through one central point, it becomes prohibitively expensive. And usually what happens is it's oversubscribed and you get poor performance.
Okay, so I have an option.
I mean, does that answer your question?
Okay, so maybe a little bit more specific. So I have a place down in Austin, and they're doing this gigabyte rollout. For $70 a month, you can get a gigabyte connection.
Mm-hmm.
But what I'm hearing you say is
for a consumer though, right?
yes, this is fiber in the house,
Yeah,
right?
fiber
So we
in
have
the
fiber
home.
in the house. I'm just going to flip it up. So if I'm playing a game there, I might not get the full use of that connection
So
because
so gigabit as a consumer can be relatively cheap, right? But if you're a business where you're serving tons of data, because even when you have fiber to the home, there's still a cap, right? If you start serving ISOs from your house, so people are downloading ISOs 24/7, your provider's going to call you up and be like, you're not doing that for $70 a month, right? They might not spell that out for you, but they will not allow that, right? If you're a business though, you do have the expectation that I can do whatever I want. but the connection costs a lot more. So the problem is, if I have 100 users, like you said, and those 100 users each have a gigabit to their house, and now some of those people are behind multiple layers of NAT, they have to come through me. So what do I have to have, a terabit connection to support them?
Okay.
So how am I gonna pay for that? Because you're right, because that's exactly the problem. If I'm a consumer, I can get massive amounts of bandwidth for super cheap. But if I'm the business that has to aggregate all that bandwidth into one central place, that gets really expensive.
Right.
So that's
So
the
like you said, they
challenge.
oversubscribe that business connection.
Yep.
So the gamers suffer because they're not getting the full throughput they think they should get.
Yep.
Because they have a gigabit connection. They're never gonna see the gigabit speeds because it's a gigabit.
Yeah, so that's the problem with the current infrastructure. Okay, so when I did this, I tried to think of, if somebody came to me and said, you know, okay, I'm a Linux guy and I want to start working on IPv6. You know, this is a really basic setup. So I did all this in ESX, which anybody can get for free, and basically I have a vSwitch and I have 3 VMs. So all of these guys are running Ubuntu 12.04, which is a fairly popular distro. The reason I went with 12.04 is because it's a long-term version. I don't like upgrading, you know, every couple months, because I think the latest is 13.10 or something like that. So this is really basic, but you can still learn a fair amount from it. So client server, I mean, that's pretty obvious what you're going to do there. And then this guy's also a server, but I'm using him as a gateway, firewall, NAT, DNS, DHCP, proxy, and server load balancing. So I mean, this is just to give you an idea of, you know, if I have a business, these are the kinds of things that I might want to start looking at. You know, how does that work? How am I going to run it? Because really, even doing this at a large scale, the concepts are still the same. Okay, and then using that setup, I have a couple of example topologies. So one is a really simple one. If I look at this guy on the left, I'd have a very simple setup where these two guys are on the same VLAN, they can directly communicate, and then this guy would be DNS, DHCP outside world. And then if I look at this guy on the right, it's a little hard to see, but there's different colors. Those are supposed to be different VLANs. So in other words, this guy on the right, if the client wants to get to the server, the client has to go through the firewall. So this is interesting because now I can play around with things like NAT, proxying, server load balancing. Like for example, let's say the client is IPv4 only and the server is IPv6 only. So how am I going to make that work? Am I going to do protocol translation? Am I going to proxy it? Am I going to do a reverse proxy? Am I going to do server load balancing? So I mean, you know, at home, you know, you probably wouldn't run into that. But let's say I'm a business, right? Let's say I'm a business like GM, and I have, you know, tens of thousands of servers. Well, for me to actually go deploy IPv6 or make changes on all those is pretty expensive. So maybe I'm not going to. You know, maybe I'm going to use a server load balancer or a proxy or something else. So the bigger the scale gets, you start looking at, you know, how am I going to roll this out? So I'd say with IPv6, it's not that complicated by itself. The biggest challenge is if I'm looking at rolling it out to a large company, how do I do that in a non-disruptive fashion, right? Because if I start rolling something out and I screw up my network access, I'm going to make a lot of enemies really fast, right? Because it's just like the power. If I take somebody's network connectivity away, they're very unhappy. I think is that the voice? What happens when somebody loses their network connectivity?
Yeah. I'll get throttled back.
All right, so what I tried to do is when I set up Ubuntu, I didn't do all the faults because, you know, obviously I selected some packages, but I tried to stick to a fairly vanilla installation and then document, okay, here's what I had to do, or if I had to actually get some software or configure something. So hopefully with a lot of this, if you wanted to replicate it, you could. I didn't do anything with the GUI just because the challenge with Linux and GUIs is there's a lot of different distros, and every distro has their own tools, has their own philosophy. So I try to stick more command line. That's more. There's still some differences like between Red Hat and Debian-based distros, but at least you have an idea. I made all of this Linux specific, but it's similar in Windows and OS 10. So if you deal with those two, it should at least give you an idea. So when I start up a system, and I don't do anything with IPv6, right? So all modern operating systems have had IPv6 on by default for a long time. So even if I do nothing, you'll basically notice if you look closely that I have these INET6 addresses, right? So I kind of wondered about these for a long time. 10 years ago when I started getting into this, I was looking at that like, well, what is this FE80 stuff? What is that? So these are the basics. So if we talk a little bit about what I want to try and do is do a little bit of review and try and build on it. So hopefully as we do this, it helps make it stick. So most people know IPv4 really well, so I like to compare and contrast. Right, so if we look at this loopback, right, everybody knows 127.0.0.1, and you can see from direction, right? You can see from this one on top, the loopback, that : 1/128. That's my IPv6 loopback. That's this guy on the right. Link local. So one thing, if you're a network guy, maybe a few of you are. There are some things that when you learn IPv6 will actually clarify IPv4, right? Like IPsec, for example. IPsec actually came from IPv6. IPsec was invented in IPv6, and then everybody was like, wow, that's a really good idea, so it got backported. So if you actually learn how extension headers work in IPv6, you'll be like, oh, that's why they did it like that. Because from an IPv4, it's kind of like, why did they do it this way? So the same with link local. Link local, I don't think I ever quite understood that 169.254. Like, what do they mean by that? And nobody uses it right on IPv4. But the idea with a link local address is it's supposed to only be significant in a link for the VLAN. So if I have one plain network that people are on, it should only be significant in that network. It should not be routable. Right? If I have two separate networks, the link local address space is only locally significant. It doesn't mean anything if I go to the other network. And the point of that is, if I have a link local address, if I plug my computer in, even if there's no central authority handing out addresses, if I have a link local address and all of us are on the same network, even without a central authority, if we all have a link local address, we can still talk. We can still do peer-to-peer, right, with nothing else. That's the idea of link local. So I have some basic minimal connectivity. Now it's totally misused in IPv4, but in IPv6 is actually enforced. So this idea of link local is I cannot talk off the link. If you try to do it, it'll actually be blocked. It's forbidden. So, but this is interesting because, for example, on IPv4, if I do DHCP, when I plug my computer in and it has no address, I have to request with nothing. So I rely on broadcast. It's kind of kludgy. With IPv6, I always have a link local address, right? So if I go back here, if I look at this guy, all my interfaces are going to have one of these FE80 addresses. So I can use that on the link to basically say, hey, I want a global address that I can actually get on the internet with. I'm not really going to talk about...
So is that double colon there, is that, what's the significance of the right and left of the double colon?
That's an excellent question. Can I come back to that in a few slides? Okay, it's an excellent question. I'll come back to that. That's basically, it's, let me come back before I go down that path. Private addressing, there isn't exactly private addressing in IPv6, and there's a reason for that. So anybody deal with large networks here? Okay, only a few. So what happens if I have two large networks that are both using private addressing and I merge them together? What happens? Are the addresses unique? No, they never are, ever. So it's very painful. Okay? So the idea with IPv6 is we got to get away from that. We don't want you know, an unregistered private address that's always gonna conflict and makes M&A a nightmare. So the idea with IPv6 on the right is we came up with something called a unique local address. So it's local, but it's unique. You randomly generate it, so that's this big long string. The idea being that if people actually do that, there should be little chance of overlap. So you don't get those painful experiences when you're talking to other people. So probably won't get into that much tonight, but just FYI. Public, we're going to talk about multicast is vastly improved and there's no more broadcasts. So just as a quick reference. All right, so back to the practical stuff. If I want to configure it, there's two ways I can do it from the command line. I can use my old ifconfig tool, or I can use the new IP route tools, the IP. So it's personal preference. The newer IP route tools are actually a little more powerful and a little more flexible, so you can do either way. One thing that will throw you for a loop, now in Linux, notice how it says add. Right, so when I do an IPv4 address, I don't use add. So if I do an IPv4 address for like 80 and then I change it, it replaces it. Because typically in IPv4, I only have a single address per interface. There are exceptions, but typically. In IPv6, that's no longer true. So in anything, any operating system, any device, the expectation is you have multiple addresses. So I just mentioned this because this is like a gotcha. Because somebody will say, they'll type in an IPv6 address and they're pretty long, right? So it's pretty easy to fat finger. Oh, oops, I put it in wrong. So then they'll just up arrow, you know, like fix it and then hit enter. And they think they corrected it. What did they just do? How many addresses did they have?
Now they got two.
Two, right? If they do it 3 or 4 times, now you have 4, right? So you actually have to go back and explicitly delete it. Because you can keep adding addresses. Linux by default doesn't limit you until you get to 16. Windows is 100. So that's a little different. Okay, so going back to the double colon and the format. So they're in hex because it's so big, otherwise it'd be insanely long. So that takes some getting used to. 8 groups of 4 digits, separated by colons. So it's case insensitive, but according to the latest RFC, you want to use lowercase. Anybody have a guess, especially in this room? Why would I care if it's upper or lowercase?
Keeps it from being ambiguous.
What if I'm doing auditing? If I'm doing auditing, do I care about case? Is that if I have case, then I have to use regular expressions, right? In IPv4, I don't have to worry about case. I have all my scripts that can just parse through the addresses. In IPv6, if I have case, now instead of just using a simple script, I have to use a regular expression, right? So it actually makes it somewhat more complex. So they're trying to simplify it and say, okay, instead of anybody can do whatever they want, there's actually a standard form. And the standard form, it's not like we're trying to constrain people. The idea with the standard form is that way when I'm doing auditing, when I'm doing scripting, when I'm doing development, there's one canonical form that everybody can agree on as opposed to everybody does their own thing. So that's the point of that.
Yeah, I'm not sure I really understood that, because you started saying things about the type of scripting that we use, and I just didn't, maybe I don't know enough about how scripting would be impacted by case sensitivity.
Sure, so it's a good question. So for example, let's say that I run a firewall using IP tables, and I have to give all of the access logs to an auditor. And that auditor is going to review all the access logs that show everybody that's traversing my firewall. So they're going to use some kind of a tool or a script to parse those logs. So the problem is if the addresses, if they don't have a standard form, some are uppercase, some are lowercase, then it makes that person's job a lot harder.
Okay.
Because usually auditors don't actually use fancy tools, they just do something like Excel or Excel macros. Right, I mean, to be honest,
That's
right?
probably true.
So it makes their job harder. Okay, so in terms of the double colon, because, and I have some addresses, let me skip to the next slide. Because these are so long, we can do what's called compression. So if I have a string of zeros, I can compress that into a double colon. And where that can be nice is even with this 2001 DB8, I can, instead of having a whole long address, 2001 DB8 00000:1, I can just say 2000 DB8::1. I can compress all those zeros. So for some addresses, it makes it much more readable. And then I give some examples. So I don't want to spend a ton of time on this. You know, I was meaning more throwing this in as reference. But when you actually get into it, you know, this is a good thing to refer back to, and you can find lots of online quizzes. But the idea is just, and just kind of think like in base 10, right? I can get rid of zeros on the left, but not on the right. Same thing. And then if I can compress the zeros, if there's only one, if there's all zeros between a set of colons, I can compress them. And then the only other thing that's kind of obvious if you think about it is, I can only do that double colon compression once, right? Because if I did it twice, then it's ambiguous. How do I expand it back out? So I can only do it once. All right, so just, again, I'm trying not to spend too much time on the reference stuff, but just so you know, so link local, that's the FE80. It's only valid on that one network, not routable. So that'll always be FE80. And one other small tidbit, it'll actually be FE8, like the whole network part, the first half, it'll be FE80 and all zeros. You actually can't use anything else. Some operating systems won't accept that. So it's actually FE80::/64. So that's one you'll see. The FC00/7, those are EULAs. Those are those private addresses. And you should only see one starting with FD, because FC is reserved. So again, I just throwing it in for reference. And then global. So this is another kind of confusing thing, is that I hear a lot of people say that global addresses are only allocated out of this space. So it's not that we can only use that space, it's just that's all that's necessary for now. Because the space is so huge, we don't need any other ranges. So again, we have one central authority, IANA, that hands out addresses, and so far that's the only pool they've had to allocate. So the bottom line is, when you're creating a global address, it's always going to start with 2. And it's not that it could start with 4 or 5, right, eventually, but we don't need it. It's kind of like with area codes. We don't just arbitrarily use them, right? When an area code gets filled up, then we have another one, right? We add them on demand. It's the same thing with addresses. So right now, that's plenty. So for now, it's always going to be in that range, and that's not going to change anytime soon. And then the last thing, and you'll see this in my prezo, is the documentation prefix, 2001 DB8. That's just for convenience. Because we all know that if you put something in a presentation and say don't use it, everybody will use it anyway. So this way you can't use it.
So that's a totally dead topic.
Smart thing.
Okay, so I'm gonna walk through this in terms of, I think this is some of the most practical stuff, you know, for day-to-day stuff, especially if you don't get heavy into the network side. So one thing that's a little hard to get your arms wrapped around is there's no more broadcasts. And I heard somebody make an interesting point. If you think of a VLAN, how do you define a VLAN? It's a broadcast domain, right? So, but that's only true with IPv4. What if there's no broadcast? I guess it's a link local multicast domain. So that is going to take some getting used to, because you don't realize how IPv4 centric our thinking is until you start trying to teach without IPv4. It's a little weird. So that is going to be a bit of a change. But the point of no broadcast is it's pretty common for networks to be multi-protocol. You know, that there's older protocols like SNA, or there's even still some people running IPX or DECnet. But there are some other protocols, especially if you get into industrial stuff, like, you know, I heard about Ford, right? Any manufacturing company is going to have lots of industrial protocols. So you're always going to have these multi-protocol networks. A broadcast is kind of obnoxious, because a broadcast means I send this traffic out and everybody has to process it. So if I send out an SNA broadcast, even if you don't speak SNA, you still have to process it. So it's just kind of not elegant. So the big reason why they killed broadcast is everything should be protocol specific. So you have groups. That's what multicast is for. That's kind of the logic. I spent a little bit of time on this because I hear a lot of people with IPv6, they'll be like, oh, they're trying to make our life hard. And actually, no, trying to make your life easier that was the idea. Also, broadcast is a source of a lot of problems. So if you deal with large-scale networks, broadcasts are what take down networks. If you get a broadcast storm, if you have too many nodes, because of the way address resolution works with IPv4, if I have too many nodes in a network, it can actually saturate the network and cause it not to work correctly. These are all broadcast issues. So broadcasting is generally bad news, and so with IPv6 they got rid of it. So instead of a broadcast, now we have the FFO2::1, which is all nodes on the link. And actually, a cool thing about multicast, if you set it up right, is it's routable. So I can change that to FFO5:1 and say all nodes in my site, if I set up multicast routing. So this is actually a much more flexible method, because I'll give you an example. A lot of people like to use Wake on LAN. So let's say I'm a systems administrator. I have 1,000 PCs at my company. I want all those PCs to go to sleep to save power, and then I can send out Wake on LAN packets to selectively wake them up. Well, right now I have to do directed broadcasts, which are, there's all kinds of issues with that. Well, with multicast, I could basically send one packet to a multicast address, and it goes to all those computers just like that, and there's no security risks, there's no stability or flooding risks. It works great. So this is a really nice solution. It's just going to take people a little time to get used to it. And just to give some examples, there's actually there's thousands of these addresses, but just a couple. All routers is 2, MDNS. So anybody familiar with MDNS? That's for plug and play. So for example, if I have like something like that camera and it's on a wireless network and I have my computer and they automatically start talking to each other and are aware of each other, that's typically MDNS. You'll notice it's also on Linux and OS 10. Of course, Microsoft has their own proprietary one. But that's the idea. DHCP, same thing. Okay, and then if I look, so a lot of the stuff, and actually this is not just true on Linux, this is true on all operating systems, a lot of the IPv6 stuff, you actually have to use new commands. It's just not in the legacy command. So you actually have to use the new IP command for this. So if I look at my multicast addresses, by default on my Ethernet interface, I'm going to join the all nodes address, I'm going to join the MDNS address, and this guy we'll talk about in a little bit.
So routers would join the all routers.
Yep. Yep, and if I'm running a routing protocol, I would join a group for that routing protocol. NTP, there's all kinds of services. Okay, this is another one. So are most people familiar with ARP? Okay, so some. So ARP is how I do address resolution. So if I want to transmit traffic, I need to know the actual hardware address of the system I'm sending to. That's what ARP is for. So this is actually a very major difference, very important for troubleshooting. That's why I put it in here. So if you ever troubleshoot ARP, you're typically going to do ARP-A or other ways, but that's the most common. It works in pretty much all operating systems use the same command. IPv6 is different. So if you're feeling bold one day and you really want to see if you understand IPv6, actually turn off IPv4 and see if you can get it working. And that was the first thing I did, is something didn't work, and I went to look at my ARP cache and it was empty. I'm like, how can they be talking if the ARP, because it doesn't use ARP anymore. So this is a major gotcha. So you definitely want to remember this. All right, and then I tried, again, I don't want to get too much into the details, but just from a high level, right, if this client on the left needs to talk to this server on the right, he's going to use DNS or something to look up the server's address. To actually send traffic to the server, he needs to know the hardware address of the server. So he's going to figure out, okay, the server's on my network, he's going to use ARP. ARP uses a broadcast, the server replies back, says this is my physical hardware address, the client can send traffic. Now, there's a couple things to know. One, it uses broadcast, right? That's a problem that's gone on IPv6. This is also a very important little subtle thing. ARP does not run over IP. This is a huge change with IPv6. Very subtle, but very important. Okay, if I look at that same story with IPv6, it's similar except we use NDP, Neighbor Discovery Protocol. This actually sits inside of ICMPv6. So quite a bit different, right? So NDP runs on top of ICMPv6, which runs on IPv6. So in other words, my address resolution runs over IP in IPv6. So that's a big change. That has a lot of interesting ramifications from the security side too. Now, one of the problems with IPv4, and this is especially a problem with wireless, is ideally with wireless, I want to have one big flat network. But the problem is, every time one of those clients needs to do one of those address resolutions, it broadcasts it out. So right now, if I look at IPv4, generally the biggest I can get is around 2,000 nodes, because IPv4 is too chatty. If I go bigger than that, the network collapses. It's too much broadcast traffic. So that's actually a major issue with large data centers and with large wireless networks. So with IPv6, the idea is how can we get away from that so we don't have these broadcast issues? And so what they did is they came up with something called a solicited node multicast. So what this is every machine, when you configure its address, it joins a special group, and there's going to be a really small set of systems to listen to that group. So in IPv6, when I want to do this hardware address resolution, only a small number of nodes are going to hear the request. So it's far more scalable. So actually, eventually, in the next 10 years or so, or 10 to 20 years, when we start retiring IPv4, the networks are going to be far more scalable because we won't have nearly as much broadcast traffic. And the way I actually do this, if I look at this guy, I'm going to take, well, let me back up for 1 second. So this guy right here, this is my solicited node multicast address, this FFO21. So the first 104 bits are always going to be the same. I take the last 24 bits, that's what I'm showing here. So I take the last 24 bits of my IPv6 address, and this becomes a solicited node multicast address. So it's only the last 24 bits, so there's some overlap, but very little. And what I'm showing here is, once you configure an IPv6 address on an interface, if you look at the multicast address groups that it joins, it's going to join the solicited node multicast address, so that's what that's for. All right. Okay, so a lot of tedious details. Let's get a little more interesting. So this is usually, when I think about setting up IPv6, the first thing I think about doing is, how am I going to get out to the internet? Or how am I going to get out to my network? So I do that with the router advertisement data. So I was a little surprised by this, but when I set up Ubuntu 12.04, it was not installed. So I actually had to do an apt-get install. I mean, it's pretty easy, but it was not there by default. There's a couple things. One thing I will say, because there's so many different distros, there isn't one central source for Linux that says this is how you do it. So sometimes you have to be a little patient with searching around. Actually, I found some conflicting information until I found the right one, and this varies per operating system. But conceptually, you have to have routing enabled, right? So this service or daemon, router advertisement daemon, it's a routing daemon. So when it tries to start up, if your node is not configured to be a router, it's going to say you don't have routing on. I'm exiting. So this is how you do it in Ubuntu 12. It varies slightly depending on the operating system, but you should be able to Google it if you use something else. Okay, so pretty typical for Linux or Unix. I basically have a conf file, and I put in some common parameters in here. Okay, so this is per interface. So if you're most likely going to have multiple interfaces, you'll have to have a section for each one. So the advertisement, the first one, that ADB send advert, that's basically saying, I want to send out advertisements. So this isn't exactly new with IPv6. We had this with IPv4, but it was never used. And the idea is, I have a router. When I basically plug that router into my network, that router is going to say to all nodes on the network, hey, you can use this network address. You can send traffic through me. So those are called router advertisements. and they tell the host how to configure themselves. So for anybody who dealt with IPX or DECnet, they had something very similar. So the idea is plug and play, right? I shouldn't have to set up this super complex thing. I turn on my router, I plug in all my nodes, and it just works. That's the idea with this. So on the, usually there's a lot of times there's a GUI, so you don't even have to get in all the advanced flags, but that's the big one. I try to comment this stuff. So the next two are for DHCP. We'll come back to that in a little bit. I threw in this link MTU. So this is getting a little bit into the weeds, but for anybody who sets up a tunnel to get IPv6, you might need to do this. That's why I threw it in there. Otherwise you'll have problems. So just file that away if you ever use a tunnel. This is my network prefix. So in other words, when I look at my address, there's two halves. There's the network part and the host part. It's split right down the middle. So this is telling all the hosts, and I'll come back to this in a second, use this for the network part. And then DNS servers and search lists. So I throw all this on. I basically do my service start, and then if I look at a client on the link, so obviously it's still going to have the FE80 address, but as soon as I turn that service on, now all the clients on the link, and it doesn't matter if they're OS 10, if they're Windows 8 or Linux, now they're going to configure themselves with IPv6 global addresses. And they will, if I look in the routing table, they're going to have that router as the default gateway. So it's more plug and play like. I mean, I can use DHCP, but on a basic level, it's that easy.
So back in your config file, you said 2001, let's see,
Yeah.
prefix 2001:DBA. You're advertising that that's your address, or that's the address that your provider gave you?
Yeah.
And you're handing that down to your clients inside the network?
Yeah. Yeah. So there's there's a lot of options. So this is a simple way. So the simple way would be like a provider gives you a prefix, and then you're going to configure that on your home router, and then it will just work. Actually, where it's going is there's something called prefix delegation. So your provider through DHCP will delegate a set of networks to your equipment, and then that will in turn hand it out to your inside stuff. So there's a whole bunch of different options, but again, in 90 minutes, it's trying to pick and choose one.
And that's a dynamic address? It's not a static IP address then?
Yep.
So within your network, you've got dynamic and static addresses. And your global address might change if the dynamic address changes, but your static, you use to talk to each other. Might stay the same.
Hold on one second. So the idea, here's the idea. I didn't put this in, but this is a good thing to briefly talk about. So with IPv6, the idea is that everything should be as plug and play as possible, and ideally we don't use NAT. Because at the ITF, they hate NAT, right? So the idea is, okay, knowing that, the average person now is gonna have a pretty complex home network, right? Because if I look at a typical home network, every person might have their own laptop, they might have their own tablet, they might have their own smartphone, their appliances might be online, maybe all their light bulbs are online, maybe the security system's online, right? Even just in a simple home, we're gonna have all these things on the network, right? So that's pretty involved, and maybe I even want to separate those out. Maybe I want my appliances and my kids on separate networks. So if we don't want to use that, and we want all that to be plug and play, how do we make that work? So the idea is we use something called DHCP prefix delegation. So the carrier, like for example Comcast is going to say, okay, I'm going to give a home user a /60. So a /60 in English, it means I'm going to give them 16 networks. So I basically, that's another change. In IPv6, we don't talk about addresses, we talk about networks. All networks are fixed. So the carrier is going to give me 16 networks. So I fire up my home router that I got from Comcast. It basically talks to Comcast. Comcast says, okay, you're going to use these 16 networks internally. And then it turns around and it'll figure, I mean, they're still working through some of the details, especially if you have multiple networks, but it'll then turn around and it will say, okay, your network wanted to use this prefix, and then it runs DHCP or router advertisements, and it all works automatically. So that's the idea, and they're even trying to, the next big thing is, even if you have multiple carriers, so if I have Comcast and AT&T, they're working on, HomeNet is working on right now, so that'll still all work automatically. I can share the load, I mean, that's the idea with IPv6, because for a consumer, right, if I look at my wife, she doesn't wanna screw with that. She wants to plug in the equipment, maybe she wants 2 carriers, so if, Comcast chokes because they had a bad day, then I can still watch Netflix through AT&T, right? But it just works. That's where they're trying to get to. And actually, it's coming along fairly well.
But with one provider.
So
every-
does that make
every node on
sense?
the network is gonna have multiple addresses. It's gonna have a global address and a link local address and.
Maybe more than one
Two,
global.
two nodes inside the network could use their link local addresses to talk to each other.
If they're on the same network, yes.
Yeah, and use the global addresses to talk outside the network.
Yep.
Yeah, cool.
So what happens if you have a web server inside, and how does like addresses work then for websites?
I mean, if a web server, well, you can do reservations. So just like your traditional DHCP, you could do, so the carrier could say, okay, your CPE has this MAC address, so I'm going to assign you this specific prefix and you're always going to get it. So that's actually possible. More typically, if you're hosting a web server, probably not going to be a residential type account, it's probably going to be a business type account. And then either you would get a fixed one, or more likely you would have more like business class equipment, and they would just configure it so you use these networks.
Oh, what about like a NAS or something that it's connected to the network that you would use that way, that you might use across the internet?
I mean, if it can, as long as it can do DHCP, I mean, that's what DNS is for. So you do dynamic DNS, and then you look up the name that way, and you should be able to always resolve it like that.
I mean, your 16 networks are still available out on the internet. Like, they gave you 16 networks. Those are publicly addressable networks.
Yeah, yep.
Right, so it's not like,
So it's assuming pretty much everybody has a firewall. So assuming the firewall allows it, yes. But yeah, they're all publicly addressable. That actually takes some getting used to.
What makes the firewall really very important too, because we've all been using NAT for a firewall, and it's been doing the job.
Yeah, I'll come back to that. So sorry, I didn't.
If there's so many IPv6, why are you not getting static IP address, IPv6 networks or addresses?
You could use static. So you definitely can use static. The problem with static is this, right? If we look at where things are going, I mean, the easiest example is light bulbs. I mean, just in this library alone, how many light bulbs do you think I have? Thousands?
Mm-hmm.
So if I look at my network administrators, right now they're managing thousands of devices. In a couple of years, they're gonna be managing tens of thousands, and then hundreds of thousands, and then millions of devices. So if I am one person and I have like 500,000 devices to manage, can you see how static addressing could be a challenge? So it's not like you can't do it, but the problem with static addressing is it's just not scalable. That there has to be a way to automate things, because where we're going with billions and billions of things on the network. Yeah, you have to, because we don't.
Imagine that many.
Even if we wanted to do it statically, we don't have the manpower. We don't have enough people. I mean, if you had to configure 1 billion devices, I mean, we don't have enough people to do it.
Full-time job forever.
Yeah. So it's basically forcing more automation. Okay.
Yeah.
Okay.
the address you use internally to access your printer, because it's on its own network, would be the same address you would use outside from the library to access your printer.
But I mean, if you go back, that came out in, I wanna say in the mid to late 90s. So if you were in networking before, I mean, we used to use public addresses for IPv4. And I remember when I went to school, I mean, we had all public addresses. When I went to school, private addresses didn't exist yet. So I mean, it's hard for a lot of people, but I mean, if you've been in the industry for a long time, I mean, the whole private address thing.
We've been so long going to our routers and setting, go to the little tab that has the little thing to write, for this port on the router over to this IP address on this other port internally or whatever.
As technology becomes more and more pervasive, though, I think the easiest way to look at it is like this. So we have actually a similar problem with phone numbers. We're running out of area codes. So in technology, we just think, we'll do NAT, whatever. But if you talk to somebody outside of IT and say, really sorry, but you know that house you bought in the new neighborhood? We don't have any more phone numbers left, so here's what we're gonna do. We're gonna give one public phone number for that whole neighborhood, and you're gonna be behind a PBX, and then when you know, it's not a big deal. When people wanna call you, they just call the number, they put in your, and I mean, what's the problem? But you know what, I've actually talked to a lot of non-technical people, and they look at me like I'm crazy or they're gonna kill me. I'm not taking away my phone number, right? So, that's the idea of IPv6, is we need to get back to that. That people can just, you can just call somebody, right? It shouldn't be a big deal.
That's the way you do that with phone numbers at companies right now.
Yep.
Every desk doesn't
Everybody
have
wants a
an
DID.
external phone number.
Yep. Okay, so, I don't want to spend, this is kind of a reference slide, but just so you know, so if you look at these addresses, if you look carefully, and I'll come back to this, you'll notice that there's a resemblance to the MAC. So this kind of drives me nuts. A lot of people say that we have 64-bit interface identifiers because, I don't know, the IEEE wanted to make our life hard or something like that. So again, I didn't actually explicitly put this, but IPv6 is a 128-bit address. So half is the network, and half is the interface ID, the network or the prefix, but basically how I get to you, and then the second half is the interface ID. It's always like that. So the idea is, how many people like subnetting in IPv4? Really, you like it? Okay, so I can tell you from teaching at college for almost 10 years, what is the single hardest networking concept that causes a lot of people to drop out of networking? Subnetting. It's actually, it's somewhat challenging. So on IPv6, there is no subnetting. Everything's a /64 and that's it. So that's why I don't spend a lot of time talking about it, because it's just gone. So now this is also hard for people to get used to, because IPv4, it's about conservation. So in IPv6, every network has 18 quintillion addresses. And people are like, you can't do that. That's illegal. But I mean, think of it like this. If I look at my parents live in Farmington Hills, they have 5-digit addressing, right? So 5-digit addressing, they could have 100,000 homes on their street, and they only have 5. I mean, isn't that a waste? How can we allow that? But who cares, because addressing is unlimited, right? So I mean, that's what we need to get back to. All right, so the reason we have 64-bit addresses is actually because of FireWire is the best example. So the IEEE has actually had 64-bit Macs for a long time. So if anybody has FireWire on their computer, you'll notice it actually uses a 64-bit Mac. This has been out for a long time. That's the real reason. It's not because they're trying to make our life hard or anything. It's just to accommodate everything they had. Because the IEEE saw the same thing. 48 bits is not enough. With all the devices that require a physical address, we're going to run out. So they changed to 64. So if you don't have a 64-bit address like Ethernet, then you have to add FFFE in the middle to basically convert it to a 64-bit hardware address. So that's all that is. So that's where this FFFE comes in the middle. Now, there's one more thing. When you take your MAC address and change it into an interface address, you have to flip the unique local bit. And this drives a lot of people nuts, because it's like, man, why do I have to do that? But there's actually a really good reason. So if they didn't do it that way, let's say I want to create a router. And a lot of times when I create a router, if I create a router, I'm going to make the router's address FE80::1, because it's easy, right? But if they didn't flip this bit, I would actually have to make it FE80::020000:1, right? Because I'd have to flip the unique local bit, because that's a locally assigned address. So to make our lives easy, so if we want to be able to do something like this, they basically flipped it. So this is assigned globally, right? This is assigned from the IEEE. So the unique bit should basically be 0. But we're flipping it so that if somebody assigns local addresses, it makes it easy. Does that make sense in the lower left-hand corner?
It's a shorthand way of saying it, right?
Yeah. It basically, if you're creating local addresses, it makes your life much easier. So, I mean, I know that's a little confusing, but it was actually done that way to make our life easier. So, anyway, it's just a reference. Okay, so when I look at from ifconfig, so here's my MAC or my hardware address, and you'll notice that it follows that pattern, right? I flip the unique local a bit. Here's the first half of my MAC address,
Oh,
here's
yeah.
FFFE, here's the second half. So that's where I'm getting those addresses from. So that mostly works, except for, there's two things. This address totally doesn't follow that. And I guess the other question that I usually get is, so as soon as I turned on the router for it to advertise the network prefix, all of my hosts have two addresses. Why do they have two?
Public and local.
So, if I look at it from the IP command, it'll actually show me a little more detail. One of them is a temporary address. So, because everything is, or most things access the internet, anybody see a problem if my address, and remember, my interface ID is always the same. So if my interface ID is always the same no matter where I go, no matter which network I access, anybody see a problem with that? What did I just create? Self-tracking. Right, basically, my MAC address is like a super cookie. It can track me wherever I go. Right, so in IPX, we didn't care because we didn't really have, there wasn't an IPX internet. But with IP, this is actually not a good thing. So, in order to fix that, they said, okay, well, we can't have that because then you can track everybody. So there's a second kind of address where we randomize it. So the whole 64-bit address is a random number. And it's also temporary, which is, this is a whole other can of worms, but just to make it simple, the idea with being temporary is it changes every day. So the idea would be nobody can track you and you're super secure. So, and from a security point of view, that's good. Anybody have long-lived SSH connections? Like anybody SSH to a server and leave it going for another day? Yeah, I do that. So what happens, so if I have this temporary address, and by default, all my connections use the temporary address so I am more secure, what happens in 24 hours when that address rotates? That's right, I get disconnected. Isn't that cool?
Yeah, but it was secure while you were there.
But you're very secure, so anyway.
So,
There's
question.
a whole other topic on that, but that's the idea.
So flip that around now. Something I hear is called mobile IP. So if you have a device that you want to have the same address to, there is something in IPv6 that allows you to do that. I'm curious how that works. And, so more curious really about the problem of, so now you have an ISP that you go through to get your address. You move to another location. It's like I have AT&T for my cell phone. I come to the library, I connect to their local network. How is it that do I have to have a contract with AT&T in order to connect with the library?
Mobile IP is a very, it does exist in IPv4 too, it just never really took off. And IPv6 added some nice enhancements which got backported. It's a great technology. The problem is outside of the cellular industry, nobody uses it. And it's really a shame because it's a very cool technology that could be used to solve a lot of complex problems, but there's zero, like Microsoft and Apple have zero interest in basically supporting it in their operating system. So it's very cool, but I mean, it's actually fairly complex. It'd be a whole talk just to go into mobile IP, but I don't think it'd be interesting to most people just because unless you're in the cellular space, you'll never see it. Unfortunately, I wish that wasn't true, but sometimes that's how it works. The IEEE or the ITF come up with a really cool technology, and companies, for whatever reason, just decide like, nope, I'm not going to do it.
Well, the thing is that it will loosen up their tie to you paying them to get access.
No, because they, I don't think that's done by IP. That's done by the PDP context, I think, which is different. But it's so basically with mobile IP. So I have a home. You know what? The easiest way to think of mobile IP is just like your cell number. So when I roam from tower to tower, does my cell number change? No, it always stays the same. So mobile IP would let you do that. Mobile IP would let you do that with an IP address. So it's very cool, because, you know, like, I mean, wouldn't it be nice if you could like power on your laptop and you could have an SSH session or a VPN connection or something like that? And you basically, you roam from wireless to Ethernet to 3G to 4G, go all over the place, and it just always works. Wouldn't that be nice? Just like a cell phone, but, and the technology exists, but Apple and Microsoft, they don't want to do it. So, sometimes that's how it goes. So this is my privacy address, and then, oh, sorry. Talked about all that. All right, and then, so I don't know if this is constant across Linux. I'm not sure, to be honest. In Ubuntu 12.04, the default is 2. Which means that privacy is on by default, which means that I use a temporary address. The temporary address is a random number, and it changes every 24 hours. You can also change it to 1. 1 is I have a privacy address, but I actually use the other address for my outgoing connections, which I think doesn't really make any sense. Or you can turn it off. I think you either use 0 or 2. And actually, you can use, you know, 10 and -1 if you want. I would stick with 0, 1, and 2. So some people do turn it off. So in a, I think privacy addresses, I think, are good for consumers. In an enterprise, they're a nightmare. So in an enterprise, I would turn it off, and I would use DHCP6, because you don't want everybody to have, you know, a couple different addresses that constantly change. Because then if you try and troubleshoot something, I mean, good luck.
When logging is done on the network, is the logging of, like, for outgoing requests, is the logging of the temporary address or the permanent address?
It's, the logging would be of the address you use. So the answer is it depends.
That's
And-
on the use temp address.
Right,
Yeah.
but I mean, if by default 2's on, and so 2's temporary,
Well,
because that
in
temporary goes
Ubuntu,
away
I
tomorrow.
don't-
So that's what you're saying
Actually,
about
Jim,
tracking.
I don't think it's the same in all distros. I
No?
think it's different.
Okay.
I don't think so. And also it depends on how old it is, right? Because, you know, a lot of times you have a server that works great, so you're not gonna upgrade.
Mhm.
So I guess one challenge, and this is interesting to me, so, most of what I get paid to do is either Cisco or Microsoft. So conceptually, I know this stuff backwards and forwards, but even when I was writing this presentation, it was kind of interesting because it's like, okay, I know what I want to do, how do I do that in Ubuntu 12? And that's, with IPv6, you'll find that, you know, you do it this way in this distro, you do it this way in OS 10, you do it this way in XP, you do it this way in 7, you do it this way in Server 2012, you do it this way in Cisco, this way in Juniper, this way in Brocade. Everybody's got their own. So it's not hard, but it's just, it's scale it gets, because everybody has their own, you know, twist or their own utilities or their own ideas, so. Okay, one thing I do want to mention, this is another big change to support and understand, and there are a lot of religious wars with IPv6, so this is one of them. So essentially, there's kind of this tension between, there's what I would call more of an enterprise mentality. So people that want control over everything, they want DHCP to control everything, and that's it. You know, total control. That's more the traditional enterprise. Then there's more of the consumer / educational mentality, which is everything's open, no control, decentralized, plug and play. Right? So you have these totally, and it's interesting when you go to the conferences and you'll hear like the enterprise mentality person and the university mentality person talk about the same thing, and it sounds like it's a different technology. It's just perspective. So when IPv6 came out, there was the one group that was all pro plug and play. They wanted everything to just plug in and work, right? So they want everything to be in router advertisements. They wanted to kill off DHCP. DHCP is bad news. We don't need it. It's too complex. Just get rid of it. Then you had the enterprise people that are like, you know, I only want DHCP. I don't want anything else. And they're still going at it today. And so we kind of got this compromise. So you have to have router advertisements, so like that router advertisement daemon we set up, you have to have that. So on IPv6, you cannot get a default gateway from DHCP v6, at least currently. You have to have that router advertisement daemon. That kind of makes sense, because typically I have centralized DHCP, and my local router is going to know best who the gateway is. So I can kind of see that, but it does make it a little more complex. There's a little bit of overlap. So originally, if I want my parameters like DNS servers, for example, are pretty important, I had to have DHCP. Recently, in the last couple of years, they changed it, so now I can get that from router advertisements as well. But by default, most Linux distros don't support it. You have to install a utility. Windows doesn't support it. OS 10, I think they added it in 10.7. So support is pretty limited. But there's very divergent opinions on that. It just depends on what you want. I would say if you run DHCP now, I would stick with DHCP. You know, for home, you probably don't need it. Okay, so in order to make these guys work, right? So remember, there's that hook into the router advertisement daemon. So I have to go back into my conf file, and there's two flags. There's essentially the managed flag and the other flag. So the other flag is if the router advertisement daemon, if it's basically doing Slack, where it just hands out a prefix and everybody automatically configures themselves, then I don't need to get an address from DHCP. So then I have the other flag. So the other flag says, okay, I already gave out addressing, I just need DNS or whatever else. You know, maybe for my phone I need a TFTP server, for example. So what that's going to do is it's going to tell the client sees that flag in the router advertisement, the client's going to go out and say, give me my DHCP parameters, like my DNS server. The other flag is the managed flag. If the managed flag is set, that's basically traditional DHCP. Give me my IP address and give me all my parameters. So I can have either or both set. All right, and then this is just a simple example. It looks, at least with Ubuntu, they use ISC's DHCP server. It's already built into 12, so you just have to play with it. I kind of ran out of time to actually get it to work with the service command, so I actually cheated and did it from the command line. But the configuration is pretty simple. You just go into the conf file. There's a basic one for your options, pretty straightforward. And this is a range of addresses they hand out. So I mean, obviously there's a bunch more stuff. There's man pages, but I mean, you get the idea. It's relatively straightforward. Now, another thing, remember, with IPv6, I have multiple addresses by default. So if I have my router advertising prefixes to do Slack, and I turn on DHCP to hand out addressing, which one am I going to use?
Both.
Both. So I'm going to have three global addresses. Right? It's cumulative. So every method you turn on, you're adding more addresses. So keep that in mind. Yes, sir?
Earlier, you were talking about groups, IPv6 groups.
Multicast groups, yeah.
Yeah, would the DHCP or would it be router advertising that configures that? Or is that statically configured?
So there's a lot of components. So at the simplest level, multicast just works on one network, right? So if I have a simple multicast setup, it's just on that network. So what happens is when I send out a multicast, you essentially the node has to be configured to listen for that multicast group. So, for example, with the solicited node multicast address, when I configure an IPv6 address and I join that solicited node group, then basically I'm programming my network adapter to say, hey, any packets that are sent to this group, I want.
Okay.
And so the nodes are basically joining those groups. So when somebody transmits a packet to that group, you basically, whether it's wireless, wired, cellular, you programmed your adapter to say, I want that traffic. Because by default, it's ignored. That's the difference. That's the difference between multicast and broadcast. Multicast, you have to opt in. Broadcast, you get it where you like it or not. Multicast, you have to say, I actually want to receive this. So that's at a local level, you're basically joining the group and then you're receiving that traffic. Now, if you go past the local network where you route it, then it gets a lot more complex. And that would, to be honest, that'd really be a whole talk of its own.
Sure.
Did that answer your question?
Yeah, it's statically set.
Yeah, pretty much. There are, in dynamic registration, where, like, let's say I want to create, let's say I install a video server, and I want that video server to automatically register a multicast address somewhere, and then have my clients automatically join it. I believe that's an area of work. So I think some vendors have a solution. I don't think there's a standard way to do that yet. But I mean, I think it's using dynamic DNS. So I can go, I can use DHCP, I can request a multicast group, I can then register it with dynamic DNS. My clients know to go and look for that particular name and they can join. So that's kind of where we're going. Again, so it's all automatic, but it's not quite there yet.
Okay.
Any other questions? How are we doing on time?
7 minutes.
Yeah. All right. So, just tell me when to cut off. All right, we're almost through the most part, and then the last section is more reference. So, remember I made that point of showing that when I do ARP is below IP, but when I do neighbor discovery protocol, it uses IP. This is huge. So, unfortunately, a lot of people have gotten in the bad habit, and this is a bad habit because there's kind of a mistaken belief that all ICMP traffic is bad and I should block all of it. That's a mistake. It actually breaks a lot of things and causes problems. You can get away with it in IPv4. However, if you do that in IPv6, what's going to happen to your neighbor resolution?
Bye-bye.
That's right. So it's going to work until your cache expires, and then all traffic will stop. So that would be bad. So this is a big thing for people doing security. You cannot block all ICMP. I mean, you will break your network. It won't work. So actually, there's two good references. Most people don't actually read RFCs, so I threw that at the bottom. But NIST, which is a fantastic part of our federal government, and they actually do absolutely fabulous work, and it's free. Right, that's what our taxes pay for, and their documents are fantastic. This is a great document by itself. You can just go to this one chart, and this is a bridge, it's just part of it, but this chart basically shows you, here are all the ICMP types, and here's what you have to allow, and here's what's gray. And it's basically somebody's done all the homework for you. And if you go and search, you can even find people on the internet that have basically followed special publication 800-119, and they'll say, here's a set of IP table rules to implement that. But that's where you want to start. Question?
You said before that the MTU, if packet needs to be broken down into fragments, that has to be done on the end node. It can't be done by a router.
Yep, correct.
Is that why there's an item up there that
Actually,
ICMP packet too big has to be
Actually,
transferred back and forth so that the host knows not to use a
You
big...
actually just made me very happy, because the last slide I put together today was a slide to answer that question. So I will answer that question in a minute. So the reason that fragmentation was eliminated is because fragmentation causes severe performance degradation. So if I have on a small scale it doesn't matter, but if I have a big data center like Facebook or a sizable company, and there's an MTU mismatch where I have to fragment traffic, that kills my network equipment. It kills it. So the performance tanks. And so a decision was made, and it's not one particular vendor, it's all vendors have that problem. So a decision was made, that's it, no fragmentation. The host has to do it. We push it back to the host. If it's distributed, right, fragmentation is a performance issue. It goes back to the relay. If we're doing it all centrally, it's a scaling problem and we can't do it. But if we push it out to the edges, most computers have plenty of processing power, then it's not an issue. So that's why they did that. Push it out to the edge, the problem goes away. But this is the problem to answer your question. So right now, and at least for the next 5 years, we're going to be, probably longer, we're going to be in a transition period, right? Where we're transitioning from IPv4 to IPv6. That means that a lot of people are going to be running tunnels or translation or proxies or other things like that. But tunnels especially, if I do tunneling, it changes my MTU. It changes my payload size. So here's what happens is, client sends a request, right? I try and get to this server. So I didn't show this, but the default MTU for Ethernet is 1500. So typically I have an MTU at 1500. I get to this router. The link between the router and the web server is only 1420, it's smaller. So this router is going to send back an ICMP error message saying, hey, the packet is too big. You have to fragment it so it's at most 1420, right? If that message made it back to the router, the client would automatically adjust, everything would be fine. That's called path MTU discovery, it's on by default. However, a common problem is a lot of people just block all ICMP, period. All ICMP is bad and is dropped. So that message gets dropped, never makes it back to the client. So basically it causes a black hole. The client can't talk to the server. This is actually a common problem. And I put it in the slide deck because this is a really difficult problem to troubleshoot. So I'll give you an example. I was using WebEx, and I have a tunnel at home because my Comcast business class connection doesn't have native IPv6 yet. It's coming this year. So that tunnel lowers my MTU. So when I tried to go to WebEx, I ran into a problem like this. And you know what? I couldn't figure it out. Like if I could look at packet traces and do testing, and I just guessed. I'm like, it's got to be an MTU issue. So I lowered my MTU by 40, then it worked. So these are really difficult because the problem is I don't have access to the middle of the internet, right? Or the customer's data center. I can't see what the far end MTU is. So there are some tools that can help with this, but MTU issues are pretty tough. So you'll see like at conferences and stuff, a lot of times they'll just set everybody's MTU to 1280. That's the minimum. So that way the issue goes away. So that's one solution. But this is definitely a problem.
So how do you know when to change that? If you're speaking to somebody, like your laptop is starting to be in trouble, and then the route changes, how does he know there's something in between him, a route change, and now he has to drop his?
Oh, you mean if you're going through one path and your path changes?
Yeah.
If the MTU changes, what usually happens is your session will get dropped and it'll just reestablish. Yeah, because they're you know, it depends. I mean, in an ideal world, you keep MTUs even across all the paths. But in the real world, yeah, sometimes it changes and usually the session will drop. Because yeah, you'll send a packet, it's going to be too big, so it will reset the session. All right, so most of the rest of this stuff, hopefully that helps. I mean, I didn't, that's kind of just getting started. This is DNS. The forward records are pretty easy. The reverse records are a little bit of a pain, but they're tools, right? This is why you use tools. You know, the tool, because you're two-thirds of that prefix, or at least half of that prefix is going to be constant, right? So you're going to say, okay, the first half is always this, and you can use a tool to automate this. But I will say that if you're a what's called a DDI vendor, so that's a vendor that makes a DNS, DHCP, and IPAM utility that automates all this, they love IPv6. Because how many people do you think are going to do these in spreadsheets? I mean, you'll do it at first, but not for long before you're going to get a tool. Okay, I was hoping actually to do some stuff with IP tables, but it's just, that'd probably be a whole other talk. But just be aware that IPv4 and IPv6, they are ships in the night. So if I have IPv4 totally locked down, nothing is allowed in, and I turn on IPv6, what just happened?
Everything's allowed in.
That's right, the whole world can go right in. That's a very common mistake. So remember, these guys, even though the IP is a misnomer.
May I have your attention? The time is now 8:30 and the library will be closing in 30 minutes at 9 p.m. Please be advised that the internet connections will shut down approximately 10 minutes before closing. Thank you.
All right, so I actually,
Yeah. They used to shut down the whole internet, now they
Yeah,
don't.
the internet's going down.
you know, I'm so used to hearing that, it doesn't even.
Yeah.
But yeah, even my son, he's like, Dad, the internet's down again. So anyway,
Especially from a kid.
So I say, fix it.
Yeah.
I mean, if you can't watch Netflix, it's a crisis. So one thing that drives me a little nuts about Linux is a lot of the utilities they add a 6 to. I don't know why they do that. I don't know why it can't just be automatic. Most other operating systems it is. I think OS 10 is like that too. Cisco and Windows are it's just always the same, but for whatever reason, that was a choice that was made, so I always forget that too, and that sucks, because you'll be sitting in iOS, and you'll do ping, and IPv6 address and it works, and then switch to Linux or Unix and it doesn't. So you just gotta kinda remember, okay, if I'm on OS 10, Linux or Unix, I gotta do ping 6. The other tools pretty much work the same. If you do network analysis, the filtering for IPv6 still needs a little improvement, but it works. Literals. So because you have colons, when you put this in a URL, you have to enclose it in brackets. So that's what they mean by literal.
Okay.
Just a good note. So, just some reference stuff. I mean, most, honestly, I don't refer to this much. I mean, usually I just Google. I know I want to do privacy addresses, Ubuntu 12 privacy addresses, and I'll come up with the right page. I haven't, in Linux, I haven't really found one book that's great for everything. I don't think it exists. It's like there's a chapter here, a chapter there. Safari's great, if you guys have heard of that, for online books, that's what I use. Okay, and then I want to talk about this briefly. So this is kind of getting a lot of publicity lately, is NAT. So, some people will say, the IETF is a bunch of priests that pontificate, and we live in the real world and we can't listen to them. But there really is a lot of wisdom with trying to get rid of NAT, because it goes back to the PBXs, right? If I'm writing an application, for example, my son's school, they have an application that calls all the parents. So if everybody has a direct line, that's relatively easy. But if all new neighborhoods are behind a PBX, and then maybe some of the smaller neighborhoods are behind 2 PBXs, how much harder does it make it to write that application? A lot harder. And all those PBXs, there's no standards, they all do their own thing, they have different delays. I mean, that's what NAT is. So NAT really makes, because in the end, we don't really, I hate to say this as a network person, we don't really care about the network, we care about the apps, right? I want to use my app. I want to go to my website, I want to use LinkedIn, whatever, right? I want to use my app, and I want the network to support it. So if the network is complicated, then instead of people focusing on making the app better, they have to waste a lot of time on infrastructure. So that's the problem with NAT. So remember, I'm not saying don't use NAT, but please, when you use it, remember what you're giving up, because you're giving up a lot. Right? So every time I help a company do an M&A and they have to do overlap NAT, the help desk, it just, they can't get it. That's an automatic escalation of level 3, right? I mean, is that what I want to use my company's money for? To pay some expert to do double NAT? So I mean, you really give up a lot and pay a lot of money to use NAT in the long run. So these are all the cases. I was actually kind of hoping to go through this. So actually, I'd be curious if somebody could tell me anything else, but I think these are all the major cases for why we use it. So it isn't just for security, it is actually somewhat useful. So, address conservation, please. I mean, somebody who tells me that we don't have enough IPv6 addresses, they don't understand math. There's way more than enough. Okay, the addressing is crazy. Topology hiding, that is a trade-off. I would argue that topology, I mean, if somebody can know your topology, first of all, you have a firewall, so you don't have to let somebody scan it. And I mean, we all have, I have a public number, and anybody can call my phone number, I cannot answer, right? Anybody can go look on Google Maps and find my house. I mean, so what? I think we just need to get over that. But I do have to admit that is one thing you lose, is you don't have topology hiding. Path symmetry is a big one. This is a big one. So if you're a smaller company and you don't run BGP, this can be a challenge. Then you basically have to do tunnels. So I still think it's worth it, but that one can be wicked, especially for smaller companies. Independence for ISPs. This is another legitimate complaint. So if I'm a smaller company, I can't go to Aaron and pay a bunch of money and get a permanent address, right? It's not going to happen. So I have to go to my ISP. So this is a drawback. If I go to my ISP and I get a public block, right, and all my systems in my company are using that public block, and then I switch ISPs, I mean, that's painful. Mm-hmm. Now, there's a lot of enhancements to IPv6 to improve that, but it's still a lot of work. So that is a major advantage of NAT, and I have not really seen a great solution to that yet. The solution I always hear is do EULAs, the FD address, do that and a global address, but that has its own set of challenges. So this is probably the biggest one. And then limited multi-homing and in-mount connections, I mean, those I don't think is that big of a deal.
Well, how about,
So, I'm not gonna go through all these, but I definitely, I wanted to throw this up. I just, you know, if you know of somebody that's using that, again, I'm not saying don't use it, there are some legitimate cases, but just always go through this. Because I can't tell you how much time I spend, you know, if somebody will deploy that, you know, how does this work? Because there's no application layer gateway for that protocol, so you give up a lot, yes.
okay, so legacy, you got, you know, hundreds, thousands of IP addresses out there that all these business partners know. You're gonna convert over to IPv6. Is this gonna be just like throw all that 4 away and give them new addresses?
No, I mean, no, it's gonna be a slow transition. But I can tell you, for example, if you look even in Michigan, right, we have a lot of companies that have B2B relationships with China and India. China and India ran out of public addresses in 2011. They have no more. So there are companies right now in China and India that are IPv6 only. So, I mean, so far, you know, we've been working around with translation and stuff, but that's actually becoming a problem. So, and that's gonna spread over to here. So, I mean, it's not, you know, nobody wants to switch, but there's just, you know, there's not enough addresses. Yeah. If you're out, you're out, that's it. All right, so the rest of this stuff is really, there's more stuff.
Another
Few
presentation.
slides.
Yeah.
Before next year.
Yeah.